So we're on lesson task number 8. We are 3/4 of the way finished with all of the lesson tasks, and it's all about solving equations, trigonometric equations. The difference between what we've done earlier in chapter 7, which is proving a statement, is that when we're working with solving trigonometric equations, we can assume both sides of the equations are true. When we work with proving a statement, you cannot assume one of the side is true. You have to assume that it's not true or assume you do not know anything about it and work with one side until you reach your destination. This is a more logical and philosophical standpoint, but it holds merits. So, let's work with solving a trigonometric equation. Suppose I had 1 plus sine theta is equal to 2 cosine squared theta. So already you see some issues over here. And you might be able to see below this what the approach should be, but in general, same with solving an equation, you like to have all your variables on one side, and you would prefer to work with one specific type of variable. In this case, our variable is theta, but we're not going to view variables just yet. We're going to look at our functions. We need to, in particular, move all the functions to one side of the equations, and they should be the same functions if possible. So I have 2 cosine squared theta on the right side. I can turn that into a sine theta using the Pythagorean identity. In doing so, I have 1 plus sine theta equals 2 times 1 minus sine squared theta. Now I can move everything over once I distribute it out. If I distribute it out, move it all over, I get all the way over here 1 plus sine theta minus 2 plus 2 sine squared theta equals 0. The reason why we move it to one side is because our terms, the highest exponent is 2. This is a quadratic equation, so you have to recall on pre-cal algebra. You like to set everything equal to 0 because in a quadratic equation, to find the solutions, you're finding the zeros, the x-intercepts, all of that good information. So, over here, I combine like terms and whatnot. I have 2 sine squared theta plus 1 sine theta minus 1 equals 0. This should look familiar. This is actually factoring. You can factor this expression. It's a trinomial with the highest degree 2. So, if I decide to factor it out, I'm going to factor by grouping. You guys might factor by some different methods and whatnot. Just provide proper justification. So if I factor by grouping, I look at this A term and the C term. I look at the first term over here, the leading coefficient and my constant. I'm going to multiply them together. 2 times negative 1, well, that's going to give me negative 2. So now I got to look at the factors of negative 2 that adds up to positive 1, which is my middle term, that B term that you've seen in pre-cal algebra. All right? So I realize that my factors that multiply into negative 2 that adds up to positive 1 is positive 2 and negative 1. Now I can reconstruct my entire expression. I keep everything the same except for that middle term. I'm going to replace it with those factors, which are going to be 2 sine theta and minus sine theta. Positive 2 and negative 1, I'm sorry. And then I'm going to group them together. I have 4 expressions. I can group them together. Boom. Now, be careful. The negative does belong with the sine theta over here. It does belong with it. So you have to keep it with it when you group things up. Now, of course, when I'm grouping things up, I'm splitting them between terms, so I'm not turning into multiplication. I'm just splitting them up. So that means I have to put an addition sign there in the middle. So, boom. Have that. Now, with these 2 giant groups, I can find the GCF of each. In the first group, the GCF is 2 sine theta. They both have a sine theta, and they both have a coefficient of 2. If I factor that out, I'm left with sine theta plus 1. Now look at the second group. In my second group, I want it to look like sine theta plus 1. I want it to be in the same form as this guy right here. So what I'm going to do is factor out a negative 1. If I factor out the negative 1, I get negative 1 times sine theta plus 1. Now they are the same. And the reason for this is now I can view this as 2 giant groups where they have a GCF again. They have a factor in common. That factor in common is the sine theta plus 1. So let's factor that guy out. If I factor a sine theta plus 1, I'm left with sine theta plus 1 times, well, the first term, if I take that away, I'm left with 2 sine theta. The second term, if I take that away, I'm left with a minus 1 equals 0. Now, this is all one singular term if I treat them as two entities. And the reason why it's one term is because there's multiplication. There's no addition, there's no subtraction, which means I have something times something equals 0. When does that ever happen? One of them have to be equal to 0. So set them both equal to 0. If I set them both equal to 0, I solved it out and whatnot, all of that. I solved for sine theta. Now I have to find the solutions for theta. Now be careful. This is not calculating inverse functions exactly. There's a huge difference between calculating sine inverse of a side ratio and sine theta of that side ratio. The main difference is if you're solving for sine theta equals a value, you apply the inverse property, which means you have infinite solutions. Infinite. If I apply the sine inverse function into a side ratio, I cut off every single value except for one unique solution, so it's a function. So in this case, I have to list all of my results. If I list all of my results, I have theta is equal to 3 pi over 2 plus 2 pi k. Where did I get 2 pi k? Sine has a period of 2 pi, which means that angle should repeat every full rotation. Similarly, I have another set of infinite solution over here, whereas pi over 6 plus 2 pi k and 5 pi over 6 plus 2 pi k. How did I get 5 pi over 6? So if I look at my unit circle right here, I know that sine theta is equal to 1/2. These are my y values at 1/2. I have to figure out what the angle measurements are for them. So the first one's pi over 6 because this should be 30 degrees if we turn it to degrees, and your opposite is 1/2. So it's going to correspond to the lower angle measurement. And then over here, to calculate this piece, to calculate that piece over here, sorry about that, this angle measurement, what you need to do is realize that, hey, this is just using the reference angle minus pi or 180 degrees. So I'm just going to do 30 minus, 180 minus 30, or pi minus pi over 6, which I get 5 pi over 6. I need to account that because every full rotation I will have both angle measurements equal to sine 1/2, or equal to the output of sine 1/2. I'm wording that incorrectly, but that's the idea. So let's work on another problem. I have sine 2 theta minus cosine theta. Now, we like to have all of our trig functions the same, so I need to turn this sine 2 theta into a cosine theta. The best way to do that is a double angle formula. So if I use a double angle formula, I turn it into 2 sine theta cosine theta minus cosine theta equals 0. I can factor out by GCF, greatest common factor, of cosine theta. Boom. I'm left with this. Now we just have multiplication. Because I just have multiplication, I can set them both equal to 0. Boom. And then I can find the solutions appropriate. So be sure you try this out, just to be sure if you can calculate these and whatnot. But that's the idea. I have 4 sets of infinite solutions. Next, let's say I have cosine theta plus 1 equals sine theta. So in this problem, it might not be as clear because I have cosine theta plus 1 equals sine theta. I don't really have the identities to really invoke that would help me. Sure, I can express one in terms of an algebraic expression in terms of the other, but I don't want to do with square roots. So a method you can do is you can square both sides. Boom. Now you cannot do this in proving. You cannot. But in solving equations, you can, but you need to be careful. When you square things, remember, there you can have the same exact value for a negative value and a positive value. What do I mean by that? I can have 5 squared gives me 25. I can also have negative 5 squared equals 25. So what that means is that you have to check for extraneous solutions if you square both sides. So I'm going to square both sides. Now if I square both sides, please FOIL it out. Don't try to square each term. Just FOIL it out and multiply it by itself. Boom, I have cosine squared plus 2 Cosine theta plus 1 equals sine squared theta. I want to turn that into a cosine. That way they're all the same functions. Boom. Move them all to one side. Boom. I can factor by GCF. Boom. Now if I solve for it and everything, I have these solutions. These three. One of them is crossed out. Why is that crossed out? Well, what I'm going to do now is go back to my original problem and plug those values in to see if they work. Let's plug in 3 pi halves. If I plug in 3 pi halves to this left-hand side right here, cosine of 3 pi halves is 0, plus 1 is positive 1. Cosine of 3 pi halves is negative 1, because that's the y value. So positive 1 is not equal to negative 1. It is not a solution set. So you have to delete all, or the entire infinite set. So boom. So that's the idea. So you only have 2 sets of infinite solutions here. Pi halves plus every rotation, and pi plus every rotation. Now this k represents an integer. That just means that it's just a full rotation. That's it. The k could be 1, could be 2, could be -5, -4. It's just not a decimal or a ratio that are not integers or whole numbers or negative whole numbers, if you will. Alright, so you can also graph things together. If you want to, you can graph the function f of x equals sine of x and g of x equals cosine of x to solve for sine of x equals cosine of x. I'm not too fan of graphing because there's always issues with that, but if you can graph it and I let you graph it, then go ahead. Normally, I do expect you guys to be able to calculate by hand though. So, you can graph these, find the intersections, and then boom. I'll leave it as an exercise for you guys to actually graph that one out. Moving on. Alright, now I have 2 sine 3 theta minus 1 equals 0. Some of you guys might be thinking, hey, I could probably use the double angle formula and then use the sum of sines. That's a bit too much. And the reason why is because I only have one function right now. I don't have a cosine theta anywhere. I don't need to invoke my identities at all. What I could do is just set or solve for sine 3 theta. I have sine 3 theta equals 1/2. Now you can do what some of you guys did for vertical asymptote. You can solve for that angle measurement. So you can set 3 theta equal to, well, at 1/2, you should have pi over 6. And then the other one is 5 pi over 6. So you can set 3 theta is equal to pi over 6 plus 2 pi k and 5 pi over 6 plus 2 pi k. And then to solve for theta, you just divide everything by 3. Boom. I just divided by 3. And there is your sets of, or there's your infinite solution sets. Next one, same exact idea, but this time I have theta divided by 2. Will I be using the half angle identity? No. There's only one trig function here, so I don't even need to do it. I can just solve for it. So boom, boom. I set it, solve for tan theta divided by 2. And then I can just solve for it. I know square root 3 over 3, well, it's located at pi over 6. It's also located at, pi over 3 really. I don't need to say the other one because tangent has a period of every pi. Because as of a period of every pi, I'm just going to do pi over 6 plus pi k. I don't need to have 2 other solutions, sets of solutions for tangent in particular. I only need one. Because once I cover half of a circle, I get to the next solution. And now I'm going to multiply everything by 2. Multiply everything by 2, I get pi over 3 plus 2 pi k. Then the question is, what if I ask, how do you find theta, or find the angle measures between 0 and 4 pi? Well, you start from 0, and then you see this guy, and see what the positive value is. Set k equal to 0. So your first solution should be, not this guy. Let's set this guy equal to 0 for k. If I set k equal to 0, I have pi over 3, my first solution. That does live in between 0 and 4 pi. Now set k equal to 1. 7 pi over 3, is that in between 0 and 4 pi? Yes. Now if I go any higher, it does not live in that region, so I'm left with just these 2 solutions. That's pretty much it after that. So the key takeaway I want you guys to think about with these is that you're going to have these infinite solution sets and, determine if you need to use an identity or not. You want to use an identity if you have more than one trig function within your trigonometric equation. If you don't, you can just set it equal to You can just isolate it, solve for it and whatnot, solve for the angle measurement afterwards, and then you're good to go. Just make sure you are very careful with this, and if you have extraneous solutions, check for it, like how we squared over here. If you're going to be squaring something, if you're going to be doing any sort of, multiplying by a reciprocal or whatnot, you want to check for extraneous solutions just in case. If you're ever unsure, just plug it back into the original and see if it checks out. So that is all for today. I will catch you guys next time. Take care. Bye.